In this video, I'd like to review with you our greatest common factoring method when it comes to factoring polynomials. First, we'll remind ourselves that factoring in general is the reverse process of multiplication. This is sometimes called the inverse or opposite. So multiplication is the inverse or opposite or reverse process of factoring. The greatest common factor, or GCF as we call it, is the greatest or largest factor, the greatest or largest factor that divides evenly into each and every term. Now, in order to find the GCF for a polynomial, we walk through a few steps here, and the first one would be to find the GCF for the coefficients. And remember, the coefficients are the numbers in front of our variables. So find the GCF for the coefficients first. That's the largest number that goes into all of the coefficients. And a good way to do this is by using a factor tree. I'll show you what that is in just a moment if you're not familiar with that. Then we will find the GCF for all of the variables. Now, the greatest common factor for the variables, or the letters in the problem, is the smallest exponent that's in common, or that's shared in common with all of the variables. You might remember that we can expand the variables by listing them out and showing the number of x's or the number of t's that are repeated, and we can count how many are common to each, or we can look at just the smallest exponent that's shared by all of them. Once we identify the GCF for both the coefficients and the variables, then we write the GCF on the left side of a set of parentheses. And since factoring is the opposite or reverse process of multiplication, we need to divide. We will divide each term by the GCF and write it inside the parentheses. And we'll use the properties of exponents to get the other factors. So let me walk through just one or two examples maybe of finding the GCF of a set of numbers, and we'll do this by using a factor tree. So I've got two numbers in each of these sets. I'm going to separate them here with this gray line, and then I'm going to build a factor tree from it. Now, the way we build a factor tree is we just look at a number and decide what are two numbers that can divide it. And in this case, 14, the first two numbers that come to mind are the number 2 and 7. And from here, we would look to see if there's any other value that can divide each of these. Now, 2 can only be divided by 2 in itself. It's a prime number, so we'll stop here. Same thing with 7. It's a prime number, so we'll stop right there. For the number 21, it can be divided into 3 and 7. 3 is prime, so we'll stop, and 7 is prime as well. Neither of these can be divided by anything except for 1 and itself. So when it comes time to identify the GCF, we look at the parts that they have in common. And in this case, the only number that they have in common is the number 7. So the GCF for 14 and 21 is 7. Now, if they had more than one part common to one another, then we would multiply each of those together. I don't think we'll see that in this example, but we might see it in part C. Building a factor tree for the number 8, I know that the numbers 2 and 4 multiply together to equal 8. 2 is a prime number. It can't be divided by anything except for 1 and itself. 4 can be divided again. That can be divided into 2 and 2, and we're at the end of the line there because we've reached prime numbers. The number 42, well, it's even, so I know it can be divided by 2, and if I check my math carefully, I know that 2 times 21 equals the number 42. 21 can also be divided again. This time 3 times 7 equals 21. Those two are prime numbers, so we'll stop there. And we will identify those that they have in common, the factors that are common to both 8 and 42. And in this case, it looks like only 1, 2 from each is common. So we would say that the GCF between 8 and 42 is 2. Now let's look at part C here and create a factor tree for each of these. I know that the number 9 times 5 equals 45. 5 is a prime number. It can't be divided any further, but 9 can be divided into 3 and 3. But 3 can't be divided any further, so we'll stop there. Now the number 75 can also be divided by 5. And 5 is a prime number, so I'll circle it right away. 75 divided by 5 is 15. That tells me that 15 times 5 is 75. So that's a good split for this factor tree. 15 can be factored again, though, into 3 and 5. And those two are both prime, so we'll stop there. Now, when we identify the GCF, I see that we have 5s in common to both 45 and 75, but we also have a 3 that's common to both. So the GCF between 45 and 75 would be equal to the 3 times 5, because each number, 45 and 75, can be factored by a 3, and it can be factored by a 5. Making the greatest common factor not 3 or 5, but actually 15, the result of the product of those two. So let's see how that plays out if I needed to find the GCF of a term that we would see in a polynomial. First, I'll just separate these two again, and looking at the coefficient 15, I'll try to find its GCF with 60. Now 15 can be divided into 3 and 5. Those are both prime numbers, so I'll stop there at the end of that tree. 60, I know that it's even, so I can divide it by 2. 2 times 30 equals 60. I'm going to circle 2 because it's prime. 30 is also an even number, so I know it can be divided by 2. 2 times 15 makes 30. And 15 can be divided into 3 and 5. Those two are prime, so I'll stop there. As far as common factors go, we have a 3 that's common to both, as well as a 5 that's common to both. So we could say that the numeric portion of our GCF is 3 times 5, which is 15. And we can also find the GCF for our variables as well. Now again, I could list these out. This x squared is the same as x times x. And this x is just 1 by itself. So I can see that there is one x that's common to both. So I know x is part of my GCF. But the other rule or shortcut that we were just talking about a moment ago is that we could keep the smallest exponent that's common to both. So if I have y to the 4th power and y squared, the smallest exponent here is y squared. And we would see that that is the GCF if I had written it out. On the left side, we'd have y 4 times, and on the right side, we'd have y twice. And the pieces that we have in common, well, 2 y's here and 2 y's there. And that's why we show that the GCF is 15xy squared. Let's try part B here as well. The number 24 has several factors. Let's start with 2 and 12. Since this was an even number, I knew that 2 went into it. 12 can be factored into 3 and 4. That's what I saw next. You might have seen 2 and 6. But I'll go with 3 and 4 here. And then 4 itself can be divided into 2 and 2. Now, no matter how you build your factor tree, when you look at the end of these branches, we should always reach the same number of primes. So you should see 3 2's and 1 3, as long as you've factored 24 correctly. For the number 36, I see immediately that this is 6 times 6, but also 6 can be divided into 2 and 3. Those are prime numbers. And this 6 can be divided into 2 and 3. When I look for parts that they have in common, we have at least 1, 2. We have a 3 that's common, and we have another 2 that's common to all of them. So the GCF, the numeric portion of the GCF here, is 2 times 3 times 2. They each have 2 2's and a 3 in common. 2 times 3 is 6, times 2 again is 12. So I know the numeric portion of our GCF is 12. And as far as our variables go, we would keep the smallest exponent. So I've got a cubed, so 12a cubed is part of my GCF. We have b to the 10th that's common to both, and that's the smallest. So we have 12a cubed b to the 10th, and then finally c to the 5th power. That's the smallest exponent there. So we have 12a cubed b to the 10th, c to the 5th power, and this is our GCF. Now we could have obtained each of these variables by writing them out. 6a's, 3a's, we would know that 3 are common. 10 b's in a row, 13 b's in a row, and we would know that 10 of those are in common. Same thing with the c value. So when it comes to actually factoring a polynomial, we use those same techniques. We're going to look for GCFs like we did in that last step, but this time we're going to pay attention to our signs here and use them to rewrite this polynomial factored. So I like to show my factor trees right here in the original problem, and I'll put the factored result over here on the right hand side. The number 3 actually can't be factored any further. The only things that divide it are 1 and 3, so I probably won't even draw that factor tree. I'll circle this because I know it's prime. The number 9 can be divided into 3 times 3. Those are both prime, so I'll circle them. And the number 15 can be divided into 3 and 5, both prime, so I'll circle them. The piece that they have in common is a 3, so we know that the GCF, the greatest common factor, the numeric portion is 3. Now I'm on the lookout for any variable that's common to all 3 pieces, and I have x to the second, x to the imaginary first, and then I have this imaginary x to the 0 power. Well, the smallest variable that goes with these exponent, or I'm sorry, the smallest exponent that goes with these variables is this number 0. Well, x to the 0 power is 1, so we have 3 times 1, or really nothing at all. There are no x's that are common to all 3 of these terms. So we'll just stop here with the GCF. As far as factoring goes, we have to list that GCF out front, in front of a pair of parentheses, and then show what's left behind after we divide each of these terms by that GCF. So let me just clean this up a little bit. I'm going to write the GCF out of the way here. And I'm going to show my work. Just my thought process here. Each term has to be divided by the GCF now. So I'm thinking to myself, what is 3x squared divided by 3? Well, I know that when I have a factor on the top and the bottom of a fraction, those two cancel out, and I'm left with x squared. Then I have the number negative 9x divided by 3. Well, again, when factors can cancel, we'll cross them out, but these two don't just cancel here. The number negative 9 divided by 3 is negative 3. But the x can't be touched. See, this reduces to 3, this reduces to 1. This x can't be touched here. There are no like terms in the denominator, so we have to leave that as 3x. And then finally, we have the number 15, positive 15, divided by 3, and we know that that is 5. So when we're looking for a factored result, this is what we get. Now, the more you practice with these, the faster you'll go, and you may not have to show all of this work here. For example, in part B, I recognize between the numbers 6 and 9, the GCF, the largest number, the GCF for number 6 and number 9 is 3. 3 is the biggest number that divides both of those. And also using our exponent shortcut, the smallest exponent that's common to both of these variables is 2, so I know that 3x squared is my GCF. With that in mind, I will list the GCF out front to the left of our set of parentheses. I want 3x squared, and then I'll show what's left behind after each piece is divided. So 6x squared divided by 3x squared. Well, 6 divided by 3 reduces to 2 over 1, or just the number 2. And x squared divided by x squared, well, x squared divided by x squared is x to the 0 power, which is equal to the number 1. So I have 2 times 1, or just 2, left behind. Then I have a negative 9x to the 4th divided by 3x squared. When I look at negative 9 divided by 3, I'm left with negative 3 over 1. So negative 3 over 1. I can just write that as the whole number 3. And x to the 4th divided by x squared. Well, this is where our exponent rules come into play. If I have x to the 4th divided by x squared, I subtract the two exponents and I'm left with x squared. So the factored result here is 3x squared times the quantity of 2 minus 3x squared. I'm going to silently work through these last two examples. Make sure that you follow along with them and add them to your notebook as well. I want to make sure that you fully understand the process here so that you can complete these examples on your own.